Welcome to the Chapter 7 of Network Plus Guide to Networks, Virtualization and Cloud Computing. What we're hoping to get out of this chapter is, as you can see here, be able to describe and explain the virtualization technologies and be able to secure those technologies, understand the different categories and models that cloud computing has really evolved into, and then be able to configure the remote connections yourselves. Now, beginning with the first chapter in our textbooks, you've created and worked with a variety of virtual machines, or VMs, in several of their capstone projects. Now, on a Windows computer, you use Hyper-V or VirtualBox to create workstation or server VMs, and you install both Windows and Linux operating systems on those VMs. By this point, you've had the opportunity to become familiar with the process and some of the terms involved in working with virtualization technology. So what is virtualization? Well, it's a virtual or a logical version of something rather than the actual or physical version. So for example, when you create an Ubuntu server, VM, on a Windows PC, the Windows machine is the physical computer or the host, and the Ubuntu machine is the logical computer or the guest that is hosted by the physical computer. The Ubuntu operating system acts as if it's installed on a separate physical machine. Now, how is that possible? Well, the key is the type of software which is known as the hypervisor, which creates and manages a VM and manages resources or resource allocation and sharing between the host and any of its guest virtual machines together. Together, all the virtual devices on a single computer share the same CPU, hard disk, and memory, and physical network interfaces. Yet, each VM can be configured to use a different operating system and can emulate a different type of CPU, storage drive, or NIC than the physical computer it actually resides on. Meanwhile, to users, a VM appears and acts no differently from a physical computer running the same software. Now, there are two types of hypervisors. Now, the type 1 hypervisor installs on a computer before any operating system and is therefore called a bare metal hypervisor. It partitions the hardware computing power to multiple VMs, each with their own operating system. Popular examples would be Zen Server by Citrix, or the ESXi by VMware, or Hyper-V by Microsoft. The second type of hypervisor, the type 2, installs in a host operating system as an application, and it's called a hosted hypervisor. Now, Client Hyper-V and VirtualBox, which you've seen in the capstone projects, are examples of two hypervisors, and as are the popular VMware and Linux KVMs. A Type 2 hypervisor is not as powerful as a Type 1 hypervisor because it is dependent on the host operating system to allot its computing power. VMs hosted by a Type 2 hypervisor are also not as secure or fast as a Type 1. VM's software and hardware characteristics are assigned when it is created in the hypervisor. Now, as you've learned, these characteristics can differ completely from those of the host machine. And keep in mind that a VM is entirely a logical entity. It's not confined to the features of the local hardware in the same way that a physical machine is. You can customize the VM with a guest operating system, the amount of memory, the hard drive space, the processor type, to just name a few options. Now here, you can see in the screen here from the VMware Creation Wizard that you can specify the amount of memory allocated to VM. Now notice in this figure, you could click on the other devices in the hardware list, such as processors, optical disk drives, and a network adapter, to make changes to those specifications as well. While there are limits imposed by the physical hardware, such as total available RAM storage, the hypervisor makes it possible for the VM guest to function differently than the host machine or other guest machines. Now, as you learn more about the virtualization, you want to train yourself to notice how logical, excuse me, how logical functions operate on a different layer or plane than what might be implied to be the physical hardware. You want to think about the foundation of a house, and in many cases, the foundation is made of cement blocks, usually reaches deep into the ground, and it defines the outline of the house to be built above it. Looking only at the foundation, however, would not necessarily indicate how many floors the house is going to have, what colors the walls are going to be, or what materials will be used on the inside of the house. On a single foundation, you might even build 2 townhouses or 4 apartments. Similarly, the physical hardware in a computer defines some outer limits of capabilities, such as how much RAM is available while running VMs, or how much storage space is available for all the VM associated data. However, within those limits, you can create many virtual machines with a variety of characteristics, and these VMs are managed by the hypervisor without being directly defined by the hardware supporting it all. Now, we have different types of network connections that we want to discuss because it's going to determine how your VM will communicate and interact with the host machine. Now, in Chapter 5 project, you set up an FTP server um, in an Ubuntu server. You might remember that troubleshooting tips for this project, which explained that if you were using a VirtualBox, you had to enable bridge mode on each VM's network adapter. So let's talk about what that means. Every VM has its own virtual network adapter, or VNIC, that can connect to the VM to other machines, now both virtual and physical. Now, just like a physical NIC, the VNIC operates at the data link layer and provides the computer with network access. Now, each VM can have several VNICs, no matter how many NICs the host machine has. The maximum number of VNICs on a VM depends on the limits imposed by the hypervisor. So, for example, VirtualBox allows up to 8 VNICs per VM. And VMs can go through a virtual switch on a host computer, like we are seeing here, to reach the physical network and communicate with physical or virtual routers. No other network device is another host on the local or another network. So, for example, here, a VM on a host A can communicate with a VM on host B. Now, the way a NIC is configured determines whether the VM is joined to a virtual network or attempts to join the physical LAN that the host machine is actually connected to. Now, these various configurations are called networking modes, the most common of which are bridged and NAT, and host only. Now, these descriptions are specific to Type 1 and Type 2 hypervisors. However, Type 1 hypervisors offer these and other network configurations as well. So first, let's take a look at bridged mode. Now, in bridged mode, a VNIC accesses a physical network using the host machine's NIC. And as you can see, the virtual interface and the physical interface are bridged together. So if your host machine contains multiple network adapters, so for example, a wireless NIC and a wired, you can choose which physical adapter to use when you're bridging to the virtual adapter. As you can see, you have VM1 is 192.168.1.132, and VNIC 2 is 192.168.1.33. 133. Now, although a bridge VNIC communicates through the host's adapter, it obtains its own IP address, its own default gateway and subnet mask from a DHCP server on the physical LAN. So, for example, suppose your DHCP server is configured and assigned a range of 192.168.1.120 through 254 to nodes on your LAN. The router might assign the host machine an IP address of 131, and a guest might get 132. The second guest on that host might obtain 133, and so on. So when connected using bridge mode, a VM appears to other nodes as just another client or server on the network. The graphic you're seeing here is from VMware, and as you can see, we're in bridge mode, and then you could click the configure adapters and then choose what adapters you want to be using. In NAT mode, the VNIC relies on the host machine to act as a NAT device. So in other words, the VM obtains IP addressing information from its host rather than a server or router on a network. Now, to accomplish this, the hypervisor acts as its own DHCP server. A VNIC operating in NAT mode can still communicate with other nodes on the network and vice versa. However, other nodes communicate with the host machine's IP address to reach the VM. And the VM itself is invisible to nodes on the physical network. Here, this illustrates a VM actually operating in NAT mode. The physical NIC has an IP address of 192.168.1.131, but the virtual machines obtained their IP address from the host as being its own virtual DHCP server, and as you can see, they are on a 10. network, 10.1.1.129 and 128. Once you've selected the NAT configuration type, you can then configure your pool of IP addressing available in the VMs on a host. So, for example, as you saw in the previous in 7.9, that your host machine has an IP address of 1.131, and you configure the host DHCP to have a range of 10.1.1.120 through 254. And then any of the VMs that you create on that host will then pull from that pool. The NAT connection type is appropriate for VMs that do not need to be accessed at a known address by other network nodes. So, for example, virtual workstations that are mainly used to run standalone applications or serve as test beds to test applications or operating system installations. They're good candidates for NAT network connections. The next one we want to discuss would be our host mode. Now, in host-only mode, VMs on one host can exchange data with each other and with their host, but they cannot communicate with any nodes beyond the host. So in other words, the VNICs never receive or transmit data via the host machine's physical NIC. As they would say in NAT mode or bridge mode. VMs that use the DHCP service in the host's virtualization software to then obtain IP address assignments. In this example, the host-only option creates an isolated virtual network. Host-only mode is appropriate for test networks, or if you simply need to install a different operating system on your workstation to use as an application that is incompatible with your host's operating system. Obviously, because host-only mode prevents VMs from exchanging data with the physical network, this configuration cannot work with virtual servers that need to be accessed by clients across the LAN, nor can it be used for virtual workstations that need to access LAN or WAN services. Host-only networking is less commonly used than NAT or bridged networking. Virtualization software gives you the flexibility of creating several different types of networking Virtualization software gives you the flexibility, of creating several different networking types on one host machine. So, for example, on one host, you could create a host-only network to test multiple versions of Linux. On the same host, you could create a group of Windows Server 2016 machines that are connected to your physical LAN using the bridge connection type, or rather than specifying one of the four network connection types described, you could create a VM that contains a virtual NIC but is not connected to any nodes, whether virtual or physical, preventing the VM from communicating with other nodes, which would keep it completely isolated. And this might be desirable when testing unpredictable software or an image of a maybe an untrusted origin. So what are the pros and cons of virtualization? Well, efficient use of resources. Physical clients or servers devoted to one function typically use only a fraction of their capacity. Without virtualization, a company might purchase 5 computers to run 5 different services. So for example, an email server or a file server, or 2 web servers, and a database server. Each service might demand no more than 10 to 20% of its computer's processing power and memory. So with virtualization, however, a single powerful computer can run all 5 of those. The cost and the energy savings alone, the organizations save money by purchasing fewer and less expensive physical machines. And then fault and threat isolation. In a virtual environment, the isolation of each guest system means that a problem with one guest does not affect the others. So, for example, your instructor might create multiple instances of an operating system and applications on a single computer that's shared by several classes. This allows each student to work on his own instance of an operating system environment. Any configuration errors or changes he makes on his guest machine will not affect the other students. Another example, network admin who want to try a beta version of an application might install that application on a guest machine rather than the host in case the untested software causes problems. Simple backups and recovery. And replication. Virtualization software enables network admins to save backup images of a guest machine. The images can later be used to recreate that machine on another host or on the same host. This feature allows for simple backups and quick recovery, such as for the classroom scenario you read about in this chapter's on-the-job story. It also makes it easy to create multiple identical copies of one VM called clones. Some virtualization programs allow you to save image files of VMs that can be imported into a competitor's virtualization program. Now, not every type of client or server is a good candidate for virtualization. However, potential disadvantages to creating multiple guests on a single host machine would include compromised performance. See, when multiple VMs contend for finite physical resources, one VM could monopolize those resources and then impair the performance of the others. Also, we had increased complexity. Now, although virtualization reduces the number of physical machines to manage, it increases complexity and administrative burden in other ways. So, for instance, a network admin who uses virtual servers and switches must thoroughly understand virtualization software. In addition, managing addressing and switching for multiple VMs is more complex than doing so for physical machines. And we'll learn more about these techniques later on. Now, finally, because VMs are so easy to set up, they might be created capriciously or as part of experimentation and then just forgotten. And as a result, the extra VMs might litter a server's hard disk and consume resources and cause other issues. It's important to understand some of the virtual functions that we have with our virtualization machines. Now, we've seen how a single workstation can host many VM workstations or servers, now each with its own network connection, operating system, and applications. Networking devices can also be virtualized. So, for example, instead of purchasing an expensive hardware firewall to protect your LAN, suppose you were to install a firewall's operating system on a VM on an inexpensive server. Suppose you also install a router VM on the server instead of purchasing an inexpensive hardware router. You've now provided your network with two sophisticated virtualized devices, a virtual firewall and a virtual router, on one expensive server instead of paying for two expensive dedicated services or dedicated devices. Now you can replicate these servers or these savings over dozens of devices for a large network, and you can begin to see some of the advantages of virtualizing your network functions. Other advantages might be virtual device can be quickly and sometimes automatically migrated or moved from one server to another in the event of a hardware failure or maintenance. Resources such as hardware, energy usage, and physical space are utilized more efficiently, and services can be easily scaled. Keep in mind when we virtualize our network functions that you will still need licenses for all the devices that you're using, especially those for a Type 1 hypervisor that will host them. Now, if we look at software-defined networking, which is what the SDN stands for, as the network infrastructures become more complex, configuring all these networking devices, both virtual and physical, and to create and manage the network infrastructure presents a much more growing challenge. Software-defined networking is a centralized approach to networking that removes most of the decision-making power from networking devices and instead handles that responsibility at a software level with a product called an SDN controller or network controller. The controller integrates configuration and management control of all network devices, both physical and virtual, into one cohesive system that is overseen by the network administrator through a single dashboard. Now, instead of reconfiguring each network device individually, the SDN controller can be used to reconfigure groups of networking devices all at one time. It can even make configuration changes automatically in response to changing network conditions. Now, if we look here on the right-hand side, you can see an implementation of an SDN. Now, instead of each device making its own decisions, the SDN controller manages these decisions for the devices and then tells the devices what to do with the data traversing the network. And what's more, the SDN controller can be programmed to change the rules for those decisions in order to adapt to changing network conditions. So, for example, if a streaming video call needs additional bandwidth, the SDN controller can temporarily assign a higher priority to that traffic across a network and then cancel the configuration when the call is finished. At no point in this process does the network administrator have to access any networking devices management console to make any changes to the device config. The SDN controller handles all the changes at a more abstracted level and informs the affected network devices of what to do with the relevant data on the physical network. Now, the network devices essentially become dumb devices without needing any particular knowledge of overarching network needs or protocols. The hardware is significantly less expensive than their more sophisticated counterpart in the marketplace. They're often called white box switches. In essence, networking devices in an SDN controlled environment function only at a layer 1 in the OSI model, while the SDN controller can manage functionality at the other OSI layers. Here we see the relationship between the physical devices and then that send and receive transmissions over the network. The SDN controller that coordinates these transmissions and the applications continuing to function at the top of the stack. Now, as you can see, one of the primary advantages to separating the control plane from the data plane is to provide network technicians with more centralized control of network settings and management. Physical and virtual devices can all be managed from a central interface. And the SDN will also create the potential to implement more sophisticated network functions while using less expensive devices. Several vendors offer SDN controlled controller software, this being VMware, Cisco, HP, IBM, and Juniper. Open source SDN controllers include Open Daylight, Beacon, and OpenShift. In recent years, the SDN architecture has been expanding to include management of network resources that are hosted in places other than an organization's own network. Now we want to take a look at cloud computing. Now, on network diagrams, the internet is frequently drawn as a cloud, where you can access information stored on web servers around the world. Now, the image captured something essential about the modern networking, and now cloud computing refers to the flexible provision of data storage, applications, or services to the client over the internet. Now, you might already be familiar with cloud storage services like Dropbox, OneDrive, Google Drive, which lets you store your own data on web-based servers. Now, web-based email is another example of cloud computing. Most cloud service providers use virtualization software to supply multiple platforms to multiple users. So, for example, industry leaders like Rackspace in its private, public, or hybrid cloud products, and Amazon in its Elastic Compute Cloud or EC2 service. Use Zen virtualization software by Citrix to create a virtual environment for their customers. Cloud computing covers a broad range of services from hosting websites and database servers to providing virtual servers for collaboration or software development. All these servers have the following features in common. They're on demand, cross-platform, means clients of all types, including smartphones, laptops, desktops, thin clients, tablet computers, all can access services. They're consolidated, which means host computers in the cloud provide multiple virtual machines, resources such as disk space, applications, and services that are all pooled or consolidated. So, for example, a single cloud computing provider can host hundreds of websites for hundreds of different customers on just a few servers. And this is called a multi-tenant service model. And there's also metered services, where everything offered by the cloud computing power, including applications, desktops, storage, and other services, would then be measured. The provider might limit or charge by the amount of bandwidth, processing power, storage, or client connections available to the customers. The elastic service and storage, here the service and storage capacity can be quickly and dynamically, sometimes even automatically scaled up or down. So in other words, they are elastic. The elasticity of cloud computing means that the storage space can be increased or reduced, and that applications and clients can be added or removed as needed. So if we took a look at a scenario where cloud computing enables a company to partner with people who are scattered across the globe, okay? So suppose an organization that develops graphic design software employs dozens of creative and highly skilled developers on a project, and these developers, half of them working from home, are located in 6 different countries. And how can these employees located so far away from the central office and far from each other collaborate successfully? Well, the company contracts with the cloud service organization to host its servers, making the company's test platform easily accessible to any of its employees via the internet. Company developers can load any kind of software on the servers, test it from afar, and share its content with distant members of the team. And if additional hard disk space is needed, that resource can be dynamically allocated. It means that the disk space reserved for the software can be increased automatically as the need arises, and then later, when it is no longer needed, that space can be freed up again for other developers. In addition, the cloud service provide services they provide makes they make sure the servers are secure and regularly backed up. Cloud computing removes the company's IT personnel the burden of managing the servers so they can focus on other priorities. The cloud computing categories or cloud computing services models are categorized by the types of services they provide. It's the National Institute of Standards and Technology has developed a standard definition for each category, which varies by the division of labor implemented. So, for example, an organization is traditionally responsible for their entire network from top to bottom. In this traditional arrangement, the organization maintains I'm sorry. For example, here, an organization is traditionally responsible for their entire network from top to bottom. In this traditional arrangement, the organization maintains its own network infrastructure devices, manages its own network services and data storage, and then purchases license for its own applications. Three of the many types of cloud computing service licenses for its own applications. Now, three of these many types are illustrated here, and these common types incrementally increase the amount of management responsibilities outsourced to cloud computing vendors. Now, to understand the various service models, it's helpful to compare them to the many ways to you acquire a pizza for dinner. On the traditional end of the scale, you can make the pizza yourself. On the other end of the scale, you can have someone else make it and serve it to you. Let's look at each service model and then explore the differences using the pizza analogy. Okay, traditional. Right, that's one there on the left. All the hardware, software, and everything else is located and managed at your location. This would be like making your own pizza from scratch at home. You provide all the ingredients, bake it in your own oven, eat at your own table. So, for example, you install Microsoft Office on your laptop, you keep all your documents on your hard drive, and then you work with Office and your documents without being connected to the internet. If we look at IaaS, or Infrastructure as a Service, hardware services are provided virtually, including network infrastructure devices, such as virtual servers and end-user interfaces, such as hosted virtual desktops. The HVDs are desktop operating environments running on a different physical computer than the one the user interacts with. These devices rely on the network infrastructure of the vendor's site, but customers are responsible for their own applications, installations, data management, desktop, backup, and possibly operating systems. So, for example, the customers might use a vendor service to store data, host websites, and provide email, DNS, and DHCP services, but could provide their own network operating system licenses and productivity software. In the pizza analogy, this would be like take and bake restaurant. You decide the type of crust you want and the toppings, and the restaurant puts it all together for you. Then you take the unbaked pizza home, bake it yourself, and eat it at your own table. In the IT world, Amazon Web Services, or AWS, is a good example of IaaS. Amazon provides the processing power, the storage space, the deployment services, and you create the VMs and choose the operating systems to install on them. You load the application, the databases, etc., and then you run the internet and other network services on those. The next we would look at would be the platform as a service. Developers often require access to multiple platforms using the development process. The platform is the context, in this context, includes the operating system, the runtime libraries, or the modules the operating system provides the applications, and the hardware on which the operating system runs. Now, rather than purchasing and maintaining a separate device for each platform, another option is to subscribe to the platform as a service. Developers can build and test their own applications. In the pizza analogy, this is The delivery option. You decide on the crust and the toppings, and the restaurant bakes it for you, and they bring it to your front door within 30 minutes. You provide your own table, and you do the cleanup after dinner. Google Platform, Google Cloud Platform, or cloud.google.com is a good example of the platform as a service. They offer pre-built VMs where you can immediately start installing and testing your software. And then the last one on our list here is a software as a service. Now, applications are provided through an online user interface. They're compatible with a variety of devices and operating systems. Online email services such as Gmail and Yahoo are good examples of software as a service. As a customer relationship management or a CRM, apps such as Salesforce and Zoho, uh, Google offers an entire suite of virtual software applications through Google Drive and their embedded products. Except for the interface itself, um, uh, the device and whatever browser software is required to access a website, the vendor provides every level of support from the network through the network administrator's infrastructure. Last, we want to look at is the anything as a service or everything as a service. In this broader model, the X represents an unknown, just as it does in algebra. It will be your variable. And I know you thought you'd never used algebra again, but here the cloud can provide any combination of functions depending on a client's exact needs. This includes, for example, monitoring, storage, applications, and also virtual desktops. Consider the service models that we're showing you here. The smaller upper end of the pyramid indicates how little the software as a service customer needs to understand and interact with the cloud provider's infrastructure in order for the customer to perform his or her work. In contrast, the IaaS customer interacts more heavily with her service provider's infrastructure and every aspect of her computing needs. The IaaS is much more pervasively integrated with the client's computer than in the SaaS. Now, at the same time, consider how accessible each type of cloud service is to end users. Here in the upside down triangle, end users' largest group of cloud computing consumers can easily access the software as a service products without much setup, where the IaaS products require extensive preparation by a much smaller group or skilled network architects and administrators who provide systems for their end users. And in the middle of the pyramid, the platform as a service, which is typically used by application developers, both professionals and laypersons, for testing their products. Customers at the lower layers of this pyramid build products that support customers at the higher layers, such as when a company subscribes to an infrastructure as a service product on which it offers its own PaaS products and its own unique market of customers. So how do we get it all out there to everybody? Well, the different types of cloud service are going to have different types of models that we're going to work with. And one of those is going to be the public cloud. Now, service provided over public transmission lines, such as the internet, is most of the examples discussed would take place in public clouds. A private cloud is a service established on an organization's own servers in its own data center. And the community cloud, where services are shared between multiple organizations but not available publicly. Organizations with common interests, such as regulatory requirements, performance requirements, or data access, might share resources in this way. For example, a medical database might be made accessible to all hospitals in a geographic area. In that case, the community cloud would be hosted internally by one of the organizations involved or hosted by a third-party provider, but it would not be made available to the public. And then we could have a hybrid cloud, which is the combination of other service models into a single deployment. Cloud connectivity and security. While cloud connectivity offers many significant advantages and opportunities for expansion, there are some drawbacks worth considering. Dependence on the internet means dependence on the network's connection to the ISP and reliance on third parties as well. Potential risk would be your ISP's uptime. ISPs impose bandwidth limitations, the cloud provider's uptime, cloud provider's backup and security, misconfiguration that exposes one client's data to another client, unauthorized access to data by cloud provider employees or by illegitimate users, breaches of confidentiality agreements, data security regulations such as healthcare and financial government entities, questions over ownership of intellectual property, questions over data maintenance if a payment is not made on time, risks to the network, proprietary data or customer information caused by bring your own cloud services on users and personal devices, reduced consumer confidence, fines, lawyers, possible criminal charges when cloud breaches occur. One way to reduce the inherent risks of cloud computing is to use encryption, which is discussed later on. Another way to carefully choose this method by which the network connects to the cloud resources. Business requirements, risk management, and cost all factor into the decision. Cloud providers will often offer attractive SLA service level agreements based on their own technology's availability. However, WAN connections that link their resources with your network is just as important. To this end, organizations generally have a four-tiered array of options: internet, remote access connections, lease line, and dedicated connections, the point of presence.